Hey everyone, welcome back to AP Pre-Calc. This is lesson 3.10. Let's get right into it. All right, so here's the bell ringer for today. Try 3-peat C because I'm about to go over the answers. All right, so for the first 3-peat here, we are given a rational function R and looking at the end behavior using limit statements. Here, we are only going to look at or care about the leading term for end behavior of rational functions. So we should have 4x to the 6 over 2x cubed, with the leading term being the term with the highest power. Then we want to simplify what we can, this fraction, because it is top heavy. So it's either going to be top heavy, equally heavy, or bottom heavy. Each one will fall in its own set of rules. 4 over 2 is 2. X to the 6 over x cubed is x cubed. And then this is going to be the end behavior of this function, will be our end behavior of this whole rational function. Here, 2x cubed, it's a positive leading coefficient at an odd degree. So this should behave like the general function y equals x, right? Which has the same properties there. This end behavior, the limit as we go to the left forever, this is going down. And as we go to the right forever, this is going up. So A would be our correct answer here. All right, number 2, which of the following is a solution to this equation? So first, I see two things with the same base. So I want to get it to one logarithm. So I'm going to rewrite this as log base 2. And remember, when we subtract two logs with the same base, you divide the insides. So x over 4 equals 1. Then a lot of people got confused what to do from here. Here, you're going to convert it from logarithmic, which is, remember, log base a c equals b, into exponential. So 2 to the power of 1 equals x over 4. 2 to the power of 1 is just 2. And then multiply both sides by 4 to get 8 equals x. And that should be our answer here, D. Number 3, this is going to be one that gave a lot of people trouble too. We have a trig function. What could be an expression? So we want to take a look at these answer choices. We see they all have an amplitude of 3. Right? So that's really not going to help us. They all have a midline of 0, which isn't shown but is implied. That won't help us either. And they all have the same b value of pi over 2. Right? So that won't help us either. So we just want to look at the starting points of each. So remember, for a positive sign, you're starting at the midline going up. For a negative sign function, you're starting at the midline going down. For a positive cosine, you are starting at the maximum and going down. For a negative cosine, you are starting at the minimum and going up, right? So all of those are really important to know. Let's take a look at the starting point for each one and then see which one maps to the actual graph that we have there. So let me do a different color for each one. Let me also highlight first the midline, the max, and the min, just for us to have. Let's do A first, so we'll do this one in red. This is a positive cosine, and it's starting at, here we see x minus 2 as the horizontal translation, which means we are going to start at 2. So this should be right here, and this is going down. This does not align with the graph, and so we can eliminate A as our possible answer choice. Here in yellow, we have this one. This is a positive cosine starting at 3 to the right. That would be right there. That does not align with the graph, so we can eliminate B. C here, this is a positive sine graph, and we're starting at 1. This would be a positive sign, would be at the midline going up. That's not the case, so it's not C. And so D here, a positive sign starting at 3, that does align with the graph, right? And so D would be our correct answer there. All right, so consider the following two equations, right? If we have sine of x equals 1/2, that's one equation. And then equation number 2 is doing the inverse sine of 1/2 equals x. Are these two equations the exact same? And so think about it for a second. Pause the video now if you need to. The answer is no, they're not. And so let's take a look at the solution to equation 2 first. since we just did inverse trig last time, here, this has an exact answer, right? We would look at the domain for sine, which would be these two quadrants. Sine's positive there and negative there. I see a positive trig value. So it's going to be in the first quadrant, and that is a 30-degree reference angle. So here we should have x equals just pi over 6 as our only answer. However, take a look at this equation here, right? Does not involve inverse trig. So what would the solution be? And this is how we would find the solution, right? When you're just solving the equation sine of x equals 1/2, this is going to be very different because there are multiple angles where if you just have sine of x that equal 1/2, right? We know at pi over 6 that has a sine value of 1/2. We know at 5 pi over 6 that has a sine value of 1/2. And I know what you're thinking. Well, what about inverse sine of 1/2 equals pi over 6, right? It doesn't include 5 pi over 6 in the solutions, but that's because we're using inverse trig. So this is inverse trig, which means when you're doing the inverse trig, to make the function invertible, we restrict the domains, we cut out a lot of solutions. However, this is what we're going to call general trig equations, there's no inverses. There's no invertibility rules that we have to test. And so any angle will go as long as it produces a sine value of 1/2. And so here we could say pi over 6, we could say 5 pi over 6, just on the unit circle from 0 to 2 pi. However, that's not our only solution. In fact, there are infinitely many solutions to this equation. If we have sine of x equals 1/2, looking at that unit circle, right? At 30 degrees or pi over 6, that's one solution. I'll use a different color. In green, 5 pi over 6, that's another solution. So here we have 5 pi over 6, you have pi over 6 as a solution, right? Let's see if we can find a few more. Here, if let's say we go one full rotation and then we go 30 more degrees, that's going to be 13 pi over 6, just if you keep counting from the radian lesson. That's one solution. Let's say you go one full rotation and then you go 5 pi over 6 more. That's going to be, should be 17 pi over 6. And that's going to be another solution there, right? And so we are coming across multiple and multiple solutions where you can basically add or subtract any number of revolutions and create technically infinitely many solutions to this very general equation without a whole lot of restrictions on invertibility or domain or range. So how can we write all of these solutions without, spending hours and hours writing as many solutions as we can think of? Well, here we can just use the two values from 0 to 2 pi, which would be x equals pi over 6, and then x equals 5 pi over 6. We're going to use these two values, and then we want to say plus or minus any number of full rotations. So we're going to say plus 2 pi k to both of these, where k is going to be an integer, and so that will produce multiple solutions. So this is how we would write it, right? If we just had this equation, we would write x equals pi over 6 and 5 pi over 6. So you have to write two separate equations, one for each value between 0 and 2 pi, and then plus 2 pi k, where k is an integer. When you write your answers, you do not need to write this part, but no, k is an integer in this case. But on the AP exam, they will not take off points if you do not specify that k is an integer. All right? And so let's take a look there. Let's take a look at the next one, which is cosine. X equals 1/2. I know cosine equals 1/2 at pi over 3, right? A 60-degree angle. And then all students take calculus at 5 pi over 3. So here x equals pi over 3, and then x equals 5 pi over 3 we see. And we can add or subtract any number of full revolutions, so plus 2 pi k, plus 2 pi k, and that will give us our answers to that equation, right? That includes pi over 3, it includes 7 pi over 3, it includes 13 pi over 3, right? All those solutions are encompassed in that. If we take a look at tangent now, tangent is special, and so because the period of tangent is pi, not 2 pi, we only need to put plus pi k and find one solution. So let's take a look at like when tangent is 1. I know tangent is 1 at a perfect 45-degree angle. And so here it would be pi over 4, which is right here. But because the period of tangent is pi, you could just say, instead of adding a full circle, you could say adding half circles, right? Plus pi, where k is 1, this then becomes 5 pi over 4. Let's say you add another half circle. That takes you back, and you're doing one full rotation like that. Let's say you add another half circle. You're going one full rotation plus 5 pi over 4. Okay, so there, just remember tangent because the period is pi, right? Your b value equation is different. Same thing here. It's pi over 4, or whatever your solution is, and then plus pi k, where k is an integer there. All right, so let's try example 1. Find all solutions to cosine of x equals negative root 2 over 2. So here I know cosine is negative in the second and third quadrant. And then cosine is going to equal negative root 2 over 2 at 3 pi over 4 and 5 pi over 4 at 45-degree reference angles in those two quadrants. So I'm going to say x equals 3 pi over 4, and then x equals 5 pi over 4. But we want all solutions. So here it's going to be plus 2 pi k because it's cosine there, and that should be our answer. All right, so let's try examples 2 and 3. Here we're also looking for all solutions. So find all solutions where sine of x equals negative 1. Here I know sine is equal to negative 1 at exactly 3 pi over 2. There's only one solution on the unit circle from 0 to 2 pi. So we're only going to have one equation, 3 pi over 2 plus 2 pi k. The next one is find all solutions where tangent of x equals 1 over root 3. This, remember, is root 3 over 3, so whichever way you want to memorize it. Here, we only need one equation for tangent, and so this should be a 30-degree reference angle, so pi over 6, and then this is going to be plus pi k, not 2 pi k, because it's tangent. All right, now number 4, this is going to be something new where we now are asked to find all solutions, but only over a specific interval. Typically, it will be from 0 to 2 pi, but you could see from 0 to pi. I've seen from 0 to pi over 2 on exams before. So just make sure you really look to see if there are domain restrictions. With domain restrictions, we're only going to want, it's going to be a limited number of angles. So we're not going to have to add that plus 2 pi k or plus pi k for tangent on these questions. Here, you're always going to start by trying to isolate this trig function. So let's do 4a together. Here, we're going to subtract root 3 to start. So 4 sine x equals negative root 3. And then we're going to divide by 2. Sine x equals negative root 3 over 2. And now sine of x is equal to negative root 3 over 2 at, it's going to be a 60-degree reference angle. So it's going to be x equals 4 pi over 3, comma 5 pi over 3. And that should be our answer there. For b, we have 6 cosine x equals, and then I'm going to add 1 to get 3. Cosine x equals 3 over 6, which is 1/2. And then I know cosine x equals 1/2 at a 60-degree reference angle, and cosine's positive in the first and fourth quadrant. So here, this should be pi over 3, and 5 pi over 3 should be our answer for 4b. All right, now we have 4c. This should be subtract 7. So 4 tan x equals negative 4, then divide by 4 there to isolate the tangent. So tan x equals negative 1. I know that tangent of x will equal negative 1 at 3 pi over 4 is the first time that that happens. So x equals 3 pi over 4. And it's also going to be at 7 pi over 4. So remember, we can't add the pi k anymore. It has to be the two exact angles. For 4d, we're going to subtract 5 from both sides. So root 3 tan x equals 6 minus 5 is 1. Then divide by root 3. Tangent x equals 1 over root 3. This should be equal to 30 degrees. So tangent is positive 30 in the first and third quadrant. So this should be x equals pi over 6, and then 7 pi over 6 there. So those should be your answers for example number 4, where you're going to have only like 1 to 3 solutions max, I would say. All right, now be aware. So this is how you know how many solutions it has. If it contains inverse trig, it will only be one solution. If it contains a restricted domain, it will have a limited number. Typically, you'll have 1 to 2. However, sometimes you could have 0, sometimes you could have 3. If the problem contains none of these things, and it's just like sine x equals 1/2, it will have infinitely many, and that's going to be encompassed with the plus 2 pi k or the plus pi k there. All right, so when solving these equations, these are the steps I would work through. First, I'm going to ask myself, what is my domain restrictions when I solve the equation? So let's work through these steps with example 5. Here I see all values. I don't see any restricted domain, so I know I'm going to have infinitely many solutions here. Then I want to isolate the trig function on one side, so that's going to be that sine of x. So I'm going to start by dividing both sides by 6 to get sine of theta equals 3 root 2 over 6. We can simplify that into just root 2 over 2 by reducing the 3 and the 6. So that's that part done. Then we want to find the corresponding angle measures on the unit circle that satisfy the given equation. So where is sine equal to root 2 over 2? That's going to be at 45 degrees or pi over 4. And sine is also positive in the second quadrant at 3 pi over 4. Then I'm going to write my solutions, or general solutions if we have them. This one does. So here we should have two equations, x equals pi over 4 and 3 pi over 4, and then plus, and we're going to tack on that 2 pi k. And both of those equations should give us our answer to example number 5. All right, example number 6. Here we want to find the x coordinates of the points of intersection between 0 and 2 pi. This is just another question of solve for x. So here 3 plus 2 cosine x equals 2. I'm going to start by working from the outside in. So 2 cosine x equals -1. Divide both sides by 2. Cosine x equals -1/2. Once we have this, then x, we want to figure out where is cosine equal to -1/2 in the range from 0 to 2 pi. Cosine is negative, equal to 1/2 at a 60-degree reference angle. So this should be at the two 60-degree reference angles where cosine is negative. So that should be here at 4 pi over 3, and then here at 2 pi over 3. Here we're only looking from 0 to 2 pi, so that will just be our answer, 2 pi over 3 and 4 pi over 3 there. All right, number 7. Here we have 2 cosine x, and we want to set this equal to -√2 and find the x coordinates of the points of intersection between 0 and 2 pi. So divide both sides by 2 to start to get cosine x equals -√2 over 2. This is then going to be x equals, and cosine is equal to -√2 over 2 at 3 pi over 4 and 5 pi over 4. So this should be x equals 3 pi over 4 and 5 pi over 4 there. All right, example number 8 and 9. This one also has a restricted domain, so we're only going to have 0 to 2 solutions, so 3 plus 2 sine x equals 2 minus 3. 2 sine x equals negative 1. Once we have that there, then what we want to do is divide by 2. So sine x equals negative 1/2. And then sine of x equals negative 1/2 from 0 to 2 pi at a 30-degree reference angle, but it should be in the third and fourth quadrant. So x equals 7 pi over 6 and 11 pi over 6 there. Number 9, here we want to find all values in the domain that yield an output value of root 3. So we see 3 tan x equals root 3. This is going to be infinitely many solutions because there's no restricted domain. Answering this question here, we're just going to first divide both sides by 3 to get tan x equals root 3 over 3. This is the same as 1 over root 3. This is one fact that I would just commit to your memory, right? You could see either one of those is fair game, and they are the exact same. One's just what happens if you rationalize the other one, right? So this is going to be at a 30-degree reference angle. So here we're just going to want to say x equals pi over 6. And then we only need 1 because we can say plus pi k, and that will encompass here 30 degrees. It will encompass 100 or 210 degrees. It will encompass 390 degrees. All of those there are accounted for with that plus pi k for tangent. All right. And finally, number 10, when you have something other than just x or theta in the parentheses, you basically want to solve for the parentheses, set it equal to whatever your solutions are, and then solve each equation for x or theta to get x or theta by itself on one side of the equation. So I know that's a lot. Let's break this down by working through 10 and 11. Here, these are all problems that we've seen before on AP exams or practice AP exams. So we have 2 cosine x minus pi over 2 plus 5 equals 5 minus root 2. I'm going to first start by subtracting 5 from both sides to get 2 cosine x minus pi over 2, and then equals negative root 2. Then I'm going to divide both sides by 2 to get cosine x minus pi over 2 equals negative root 2 over 2. Just treating this as like x, right, or theta. Cosine of what angle will give us negative root 2 over 2? That is going to be here. So 3 pi over 4 and 5 pi over 4 should be our answer. And then here it's all values, no restricted domain. So I'm going to have x minus pi over 2. So take this whole side and set it on the left-hand side. This should be equal to 3 pi over 4 plus 2 pi k, and then 5 pi over 4 plus 2 pi k there. So let me kind of erase some of this stuff here on this side now, just to make more room. So once we have this, right, we have our two equations set. Now what we're going to do is we're going to add pi over 2 to both sides of both equations. Let me just rewrite it a little nicer there. There we go. So plus pi over 2 plus pi over 2. This will get rid of the minus pi over 2. So now we just have x. And now we want to simplify what we can. So this is x equals, and then 3 pi over 4 plus pi over 2. Pi over 2, to put it with a denominator of 4, just so we can add the fractions, is 2 pi over 4. So this should be x equals 5 pi over 4 plus 2 pi k. That's going to be our answer there. And then this is going to be x equals, and this was 2 pi over 4. So 7 pi over 4 plus 2 pi k. That should be our answer there. All right, so that was one of the harder questions. You will have one really challenging problem like this on your quiz, so be aware of that. The next one here, we have cosine 2x plus 4 equals 9 over 2. I'm going to start by subtracting 4 from both sides to get cosine 2x equals 9 over 2 minus 4. I'm going to change 4 into 8 over 2 to just get 1/2. Then what cosine of what angles equals 1/2? This should be pi over 3 plus 2 pi k, and then plus 5 pi over 3 plus 2 pi k. So once we have this, these are not our solutions because we need to solve for x. So what are we going to do? We're going to take both equations and divide it by 2. So if we take the first one, we should get x equals, and then pi over 3 divided by 2 is going to turn into pi over 6, plus 2 pi k. This will also be divided by 2, so this is going to be plus pi k. So here, notice how we didn't touch the plus 2 pi k because we were just adding or subtracting. When it is like that, you will not touch that general part, the plus 2 pi k or plus pi k. When you're multiplying or dividing, you will impact the plus 2 pi k or the plus pi k there. Here, this should be x equals 5 pi over 3 times 1/2 would be 5 pi over 6 plus 2 pi k divided by 2 should be plus pi k there. This is going to be our solutions to our answer there for example 11. All right, so picking up from day 2 where we left off, we'll start with 3-peat D. So pause the video if you haven't done this already because I am about to go over the answer. All right, so for question number 1, we have a Pascal's triangle / binomial theorem problem. If g is given by x plus 3 to the power of 6 there, what's going to be our coefficient on the term with the x to the 4th in it? So first thing we want to do is when you see a binomial raised to a certain power, whether it be 3, 4, 5, or even 6, the first thing we're going to want to do to solve this problem is draw out Pascal's triangle. And remember, this starts with ones at the top and then going down. So let's do that now. Let's add a few ones. And then remember, every number is made up by taking the sum of the two numbers above it. So there, it would be 2 is 1 plus 1, 1 plus 2 is 3, 2 plus 1 is also 3, and then we have ones on the side. This is 4, 6, 4, 1, 5, 10, 10, 5, and 1, and then one more row. We'll have 1, 6, 15, 20, 15, 6, and 1. We can kind of end here because seeing that our n is in this case going to be 6, where this is a plus b to the power of n, we are really just looking for this row right here, the row with that 6 right there. That's going to be our key. This is row 6 is what we're looking for, and then remember the top one is technically row 0, row 1, 2, 3, 4, 5, and then row 6. So that is what we want. Once we have those numbers, 1, 6, 15, 20, 15, 6, and 1, we are going to, and you'll have paper on the AP exam or scratch paper, write them down and space them pretty far apart. So 1, 6, and we'll add plus signs to separate them, 15, 20, 15, 6, and 1. And now let's identify our A and our B in this expression. So here A is just going to be x and B is going to be positive 3. So remember, if it was x minus 3, you would want to include that negative sign on the B term as well. And then we'll do each one in a different color. But we're going to start with taking our A, which in this case is just x, raising it to the power of n, and going from left to right. Here we're going to start with this x to the 6, and then decrease the power by 1 as we move from term to term from the left to the right. So this should be x to the 5th, x to the 4th, x cubed, x squared, x to the 1st, and then this is x to the 0th, which is really just 1. So a lot of times we don't even write it. You can kind of ignore that there. Now we're going to take b, which in this case is positive 3. I'm going to put parentheses around this. I technically did around the x, and then you're going to raise it to the power of 6, or n, on the right. And you're going to go from right to left for your b term this time. So here we're going to have plus 3 to the power of 6, 3 to the 5th, 3 to the 4th, 3 cubed. This should be 3 squared, 3 to the 1st, and then 3 to the 0th, which is just, again, 1. And now we're looking for the term containing x to the 4th. Looking for that, I see that this is this term right here, which is 15 times x to the 4th times 3 squared. We don't even need to evaluate any of this because our answer choices are perfectly aligned if you use the binomial theorem. So C should be the correct answer there, right? Question number 2, there's a few ways to solve this one. We basically have two functions that we want to set equal to each other, and we're solving for x. So I'm going to show you how to do it both ways in the video because I have time. All right, so first thing, we're just going to set both equations equal. So log base 2 x plus 3 minus log base 2 equals 2. The first thing I'm going to do, or the first way I'm going to solve this, is by simplifying the left-hand side by combining them into a single log. So remember, if we have the same base and we are subtracting two logs with the same base, we can divide the insides. So x plus 3 over 2 equals 2. And now we can turn this from logarithmic form to exponential. So this is going to be 2 to the power of 2 equals x plus 3 over 2. And now solving for x, 4 equals x plus 3 over 2. Here we can multiply both sides by 2 to get 8 equals x plus 3. Subtract 3 to get 5 equals x. That should be our answer. So C should be correct. And then just to make sure, if you plug in 5, you would get 8 here, but there's no domain errors, so that is all good. So that is the first way we can do it. The other way that you can solve this is log base 2 x plus 3 minus log base 2 equals 2. Here you can simplify this. We know this is just the number 1 because 2 to what power gets you 2? And that's just going to be 2 to the 1st. So you have log base 2 x plus 3 minus 1 equals 2. Here we are going to add 1 to both sides. And then now we convert it from logarithmic to exponential. So 2 cubed equals x plus 3. 8 equals x plus 3. Subtract 3 from both sides to also get 5 equals x. So that's two different ways to come to the same solution there. All right, question number 3. The function h is given by h of x is 2 times tangent of x. What of the following is your period? So remember, here in this case, our b value is very simply 1, right? There's no horizontal dilation being impacted with this equation in particular. We only see a vertical dilation, which does not impact our period. So our b value is 1. And then remember, for tangent, our period is pi, not 2 pi, over our b value, which is pi over our b value of 1. So it's just pi would be our period. So C would be our answer for number 3. All right, so now that our three-peats are out of the way, let's move on to today's actual lesson. So today we're going to be talking about solving equations that involve a whole trig function, possibly squared, and how to solve for x there. And so if we just have the variable x, right? If we want to square that, it's pretty easy. We just raise it to the power of 2. However, with trig functions, it's a little bit more complicated because the notation is very messy, right? We want to make sure our notation is clear. We communicate what we are really trying to do to our reader or to the AP grader on a free response question. And so the notation is going to be a little tricky. What I mean by this is, let's say I say these two things, right? Sine of 30 degrees squared and sine of 30 degrees squared. On paper, this looks like the exact same thing, right? What do parentheses really matter? Well, the first one here is saying we're actually just doing sine of 30 degrees, and that only the angle value is squared, which is 900 degrees. That is not what we're going to want to say a lot of the time when we're solving the equations. When we're solving the equations, we're going to want to talk about the entire trig value or trig function being squared, which is this is sine of 30 degrees squared, which is 1/2 squared, which would be 1/4, would be actually what this is equivalent to here. This is what we're going to be having or seeing in our equations a lot of times, and these two things are very, very different, but look very similar with our notation. And so we want to make sure that we communicate our intentions on what we want to express. And a lot of times, just make sure that you're talking about squaring the entire trig function, not just the angle measure. So there's two ways that we can communicate this. The first way is what you just saw, which is putting parentheses around the whole trig function, right? Maybe sine of x, and then this whole thing squared, where we are communicating this entire thing is squared. Another way to do that, or an equivalent way, is by writing sine squared x, where we move this 2 on the inside here, and you don't even need to put parentheses around it at this point. These two things are absolutely synonymous. They are the exact same. There's no difference between them. And so this is what you're going to see. You're going to see this notation more times than not versus 2 parentheses and then the square on the outside. But just know that you should never have this notation because we won't be solving any problems that involve that. All right? So real quick, what is the square root of 9, right? If I ask you, what's that? And no, it is not 3. It is plus or minus 3, right? Remember, when you take the square root of 9, this is going to be plus or minus 3, because here, negative 3 times negative 3 gives you 9, but also positive 3 times positive 3 both give you 9. So do not forget, when you take, if we have, let's say x squared equals 9, and we are solving for x, and we take the square root of both sides, here you should have the plus or minus 3 when you solve that equation in your answer. That is going to be very important and the biggest key to today's lesson, because you're going to be taking the square root of trig functions. You're going to need a plus or minus when you take the square root of a number. All right, so let's take a look at some of these problems, and I'll work through all of them together. So pause the video if any time if you need to work them out yourself, or if you need to go back and rewatch any part of these questions. All right, so for the first one here, we want to find all solutions from 0 to 2 pi. So we're going to have a limited number. That means that plus 2 pi k or plus pi k won't be needed here. We're only going to have a certain number of solutions. So let's do that with A. Here, I'm going to first start by isolating our trig function. So I'm going to subtract 3 from both sides to get 8 cosine squared x equals 2. And then I'm going to divide both sides by 8. So cosine squared x equals 2/8, which is 1/4. And now what I'm going to do is, remember, this is the same thing, and I'm not going to write this out every time, as cosine of x, and this whole thing in parentheses squared, equals 1/4. So I'm going to take the square root of both sides now. Here, I am going to get cosine of x equals, and then this is the square root of 1 over the square root of 4, which is 1/2. So should equal 1/2, but that would be wrong, because remember, when you take the square root of a number, we have to add our plus or minus. So now we have cosine of x equals plus or minus 1/2, and we're solving for x, so we're not done there. This is just a very general solution, right? And we're only looking at angles from 0 to 2 pi. So where is cosine equal to positive 1/2? Well, that's going to be at pi over 3 and 5 pi over 3. But now we have to also consider, where is cosine equal to negative 1/2? And that's going to be at 2 pi over 3 and 4 pi over 3. So that is going to be our answer for x there, all 4 of those angles. So typically, when you take the square root of a trig function like that, and you get plus or minus a value, it's going to be all 4 quadrants because it doesn't matter if it's positive or negative. So here, pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. You're probably going to get 4 solutions there. Let's try B, C, and D now. Here we have 2 tangent squared x minus 5 equals 1. I'm going to start by adding 5 to both sides. So let's do that now. Equals 6. And then here I'm going to divide both sides by 2 to get tangent squared x equals 3. Now I'm going to take the square root of both sides. Taking the square root of this, we are just going to get tangent x equals plus or minus root 3. Once we have that, tangent is going to be equal to plus or minus root 3 at a 60-degree reference angle. So here, and it doesn't matter if it's plus or minus, so we're going to take every 60-degree reference angle and include that from 0 to 2 pi. So that would be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 should be our answer for 12b there. Let's take a look at 12c. Here we have 6 sine squared x. I'm going to subtract 9 from both sides to get 3. Divide both sides by 6 to get sine squared x equals 3 over 6, which is 1/2. Then we got to take the square root, so we're not just done there. This is going to be the square root of 1 over the square root of 2, which is 1 over root 2. A lot of times this is unfamiliar, but remember, when you rationalize the denominator, right, which is get that denominator out, which in this case is just multiplying it by root 2 over root 2, this is going to be root 2 over 2, which is a more commonly known trig value. So this is the same as this right here. Those two are equal. It's just a different way to write it. So be familiar with that. Here, then we should get sine of x equals plus or minus root 2 over 2. Once we have that, it's going to be every reference angle of 45 degrees, because that's where sine is equal to root 2 over 2. So that's going to be x equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 as our answers there. All right, so that's 12c. 12d, here we have 4 sine squared x equals 3. Divide both sides by 4 now. And then take the square root of both sides. Here you're going to get sine x equals plus or minus, and then this is root 3 over root 4, which is 2. So plus or minus square root 3 over 2. This is going to be at another 60-degree reference angle. So we should get x equals, and remember the plus or minus, pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And that should be our answers there. So a lot of the time, you're going to see maybe the same answers pop up. You could also see pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6 be a common answer to these problems as well, too. All right, let's try example 13. The function g is given by that. What are the zeros from 0 to 2 pi? So let's solve this one. Here we have 3, minus 4 sine squared x, and we want to see where is this equal to 0. I'm going to start by subtracting 3 from both sides to isolate that trig function. So negative 4 sine squared x equals negative 3, and then divide both sides by negative 4. To get sine squared x equals, the negatives will cancel out, 3 over 4, and then take the square root of both sides to get sine of x equals plus or minus square root 3 over 2. And then where is that? That is going to be very similar to the problem we just solved. So it should be a 60-degree reference angle. So x equals pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And that should be our answer for 13 there. All right, now what happens if there's a cosine squared and a cosine term in the problem? We are now going to treat it kind of like a factoring problem very similar to the A method problem that we learned in 2.13, right, where we use the A to replace a log or an exponential function. We're going to do the same thing here, but replace sine or cosine theta with the letter A. Depending on the problem, we're going to factor and then solve and then substitute that cosine theta or sine of theta back in. Make sure you never divide by sine or cosine because then you're losing solutions, right? So a good example is if you have sine squared theta equals sine of theta, a lot of students just want to divide by sine theta and say sine theta equals 1. If you just only solve that equation, you would be getting the wrong answer because you would be losing solutions, and that's not what we want to do. So instead, you are going to want to get them all on the same side of the equation and then factor. So we'll learn how to work through some of these problems. That's the rest of this lesson pretty much. Let's first start off with a good exercise. So factor each of the following expressions completely. So pause the video, try this one now because I'm about to go over the answer. So here for the first one, we're going to factor out an x and then get x minus 2. Here, we can't factor anything from all three terms, so we can factor out an x, and we're going to have to actually factor this. So x minus 3, x minus 2. These two numbers multiply to get positive 6, but add to get negative 5, so that looks good there. Here, this would be x plus 3, x plus 1. They multiply to positive 3, but add to positive 4. And then here we can factor out an x to get x times x plus 4 there. Right, so that would be how we factor. This exercise will come in handy in the next few problems. So here's a good one, example 15. This is one where if you divided both sides by just cosine theta, you would get or lose solutions. So let's solve this another way. What we're actually going to want to do is move this to this side of the equation. So we have cosine squared theta plus cosine theta, when we add that to both sides, equals 0. And now let's use the A method, right? So A equals cosine theta. So we should have A squared plus A equals 0. And then factoring this, we can factor out an A and get A plus 1 equals 0. Now we have A equals 0, and we have A plus 1 equals 0. And we can sub now cosine theta back in. So here, cosine theta equals 0. And then here, you should get A equals negative 1. So cosine theta equals negative 1. And now we're solving both equations for theta in between 0 and 2 pi. So look at your domain restrictions. Once we have this, cosine theta will be equal to 0 at pi over 2 and 3 pi over 2. So that is going to be two of our solutions. Cosine theta will be equal to 1 at, or negative 1, sorry, simply at pi. So our answer should be x equals, and we're just going to combine both of these, 3 pi over 2 and pi. That is going to be our answer for 15 there. All right, let's try the next one. Here we have 2 sine squared x, and we want to see where's the intersection points for x coordinates from 0 to 2 pi. So we're just going to set both of these equal to each other. Root 3 sine x. Notice how this is not underneath the radical, so the radical does not extend. I'm going to subtract this from both sides to get 2 sine squared x minus root 3 sine x equals 0. And then use the A method, so sine x equals A. Once we have that, then we have 2a squared minus root 3a equals 0. We can factor out an a here and then solve. So kind of just setting up over here, we're going to get a equals 0, and then we're going to get 2a minus root 3 equals 0. Here, 2a equals positive root 3, adding root 3 to both sides, and then dividing by 2, a equals root 3 over 2. And now that we know that, sine of x, we're going to sub that back in for a. So here, sine of x equals 0. From 0 to 2 pi, this should be x equals 0, pi, and then it doesn't include 2 pi, so even though 2 pi is a solution, we're not going to include that in our answers. Here, solving this equation, we have sine of x equals just to only positive root 3 over 2, so we're only going to be looking at the first and second quadrant. Here, this should be at a 60-degree reference angle, so x equals pi over 3 and 2 pi over 3. And so combining these both to get our answers, we should get x equals 0, pi, pi over 3, 2 pi over 3 to get our answers there. So just like put a box around your final answer. And it doesn't matter how you order them, right? As long as I just see all the solutions, that's really what matters there. All right, so let's try 17 and 18 now. All right, so here we have same question, so we're going to set them equal to each other and solve. So we have sine of x equals 2 sine squared x. Here I'm probably going to I want to keep this positive, this term positive, so I'm going to move this to the right-hand side by subtracting sine x from both sides. And then get 0 equals 2a squared minus a, where a is sine x. And then factor, 2a minus, here we should get 2a minus 1. Solve, so a equals 0, 2a minus 1 equals 0. Here you get 2a equals 1, a is 1/2. So we have a is 0 and a is 1/2. So let's solve those now. We have sine of x equals 0 and sine of x equals 1/2. Solving them between 0 and 2 pi, sine of x is going to equal 0 at 0 and pi. Sine of x will equal 1/2 at pi over 6 and 5 pi over 6, because it should only be in the first and second quadrant at a 30-degree reference angle. And then sine your y-coordinate will be 0 at 0 and pi. We don't include 2 pi here. So our answer should be, let me make some space here, x equals 0, pi, pi over 6, and 5 pi over 6 should be our answer for number 17 there. All right, let's try 18. Here we're going to do the same thing, set each equation equal. So 4 cosine squared x plus 5 equals 8. This one we only have one term, so it's going to be a little easier to work with. It's going to be the ones that we started today with. So I'm going to subtract 5 from both sides and then divide both sides by 4. So we have a cosine squared x equals 3 over 4. Then we're going to take the square root of both sides to just get cosine x equals plus or minus square root 3 over 4, which is the square root of 3 over 2. And then here, we're going to get 4 angles. Where's cosine equal to root 3 over 2? That is going to be at a 30-degree reference angle. So it should be pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6 on the unit circle there. All right, now let's try the next two. We have 19 and 20. Here we now see a tangent one, so 3 tangent squared x minus 1. And we want to find the zeros, so we're going to set this equal to 0. And solve, so I'm going to add 1 to both sides. And then divide both sides by 3. And then take the square root of both sides. So remember, when you're doing this, this is the square root of 1 over the square root of 3, which is 1 over root 3. And then this is going to be tangent of a 30-degree reference angle. So here you should have tangent of x equals plus or minus 1 over root 3. That again, like I said, was a 30-degree reference angle. So it should be x equals pi over 6, 5 pi over 6, 7 pi over 6, and then 11 pi over 6 there. So a lot of times you'll see your domain be from 0 to 2 pi. However, sometimes they may switch up your domain as well, so always just be a lookout for that on every given problem. All right, let's try this one here. We're just solving for theta, so 4 sine squared theta equals 1. I'm going to divide both sides by 4 equals 1/4, and then take the square root of both sides to get sine theta equals plus or minus, and then this is 1 over 2, so plus or minus 1/2. And then here, sine is going to be equal to plus or minus 1/2 at a 30-degree reference angle. So this should be at 30 degrees. So it's going to be the over 6's. So pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. So that should be our answer to number 20. All right, 21. This is one where we have a restricted domain. We have from 0 to pi over 2, not our typical 0 to 2 pi given domain. So let's solve this. We have cosine squared, or cosine cubed x plus cosine squared x equals 0. So I'm going to set this just up into one equation. So cosine cubed x plus cosine squared x equals 0. I'm going to use the a method here when you have two cosine terms. So a cubed plus a squared equals 0. Here we can factor out an a squared and then solve. So a equals 0, a equals -1. And then we would get cosine x equals 0, cosine x equals -1. Here cosine x will only equal 0 at pi over 2. And then cosine x will actually never equal -1 from 0 to 2 pi, because cosine is your x coordinate, right? And this would be typically just pi, but that's not in our domain. Just like how this would also be 3 pi over 2, but that is also not in our domain. So our only answer here should just be pi over 2. And then because it's a closed bracket, it does actually include this value. So x equals pi over 2 is our only solution here. All right, and then example number 22, you will see a problem, I can guarantee you right now, very, very, very similar to this on your next quiz, where you will have to use the a method for a trig function like this. So here we have 2 sine squared x minus 3 sine x, and we want to find all inputs where this is equal to -1. So first thing we want to do is get all the terms on the same side of the equation, right? We cannot factor this left side without this being set equal to 0. That's the biggest thing, right? A lot of people want to see x squared, like plus 5x equals -6 there. And then they'll say, oh, you can factor this into x plus 5. But you really can't, because this side is not equal to 0. It needs to be equal to 0. That was just an example there. And so we need to actually add 1 to both sides here. So we have 2 sine squared x minus 3 sine x plus 1 equals 0. Now we can factor this and use the a method. So here a is equal to sine of x. We should get then 2a squared minus 3a plus 1 equals 0. This is very tricky for a lot of students to factor, right? Because you have a leading coefficient that is not 1, but I would expect you to be able to factor this. Here it's just going to be, we see they add to -3, but multiply to +1. So we're probably going to have a -1 and then a -1 there. If you FOIL it out and check, you see that that is how you factor it. So there we should get 2a minus 1 equals 0 and a minus 1 equals 0. Solving both equations, you should get a to be 1/2 and then a to be 1 there. Knowing that a is sine of x, I'm going to take those equations and work on this side here. So just moving those over to this side. We have sine of x equals positive 1/2. And then we also have sine of x equals 1. Now, the biggest thing here is what is our domain on this question? Think about it for a second, because the answer is that we aren't given a restricted domain, which means this is going to be the only problem that we've done today that will include that plus 2 pi k. That's really what a lot of students miss, and that's going to be half the points on this question. So here we're going to first just solve between 0 and 2 pi. So this should be x equals, and then positive 1/2 at pi over 6 and 5 pi over 6, and then x sine of x equals 1 at pi over 2 from the unit circle. Now that is not our answer. We are actually going to write 3 equations. Our first equation is going to be x equals pi over 6 plus 2 pi k. Our next equation is going to be x equals 5 pi over 6 plus 2 pi k. And then our third equation is going to be here, I'll write it on the bottom, x equals pi over 2 plus 2 pi k there. So all 3 of those would be part of our solutions. You need to have the plus 2 pi k. That will be half the points. You need to set one side completely equal to 0. If you don't, you'll get the wrong solutions. And so just really make sure you know how to solve example number 22 and very similar questions to that. Maybe I may switch sine with cosine or change the factoring, but the actual idea of the problem will be the same on the quiz. All right, so if you have any questions, please come see me in office hours, and I will see you guys later. Thanks.